Welcome everyone. Today we are just going to talk about some updates and then go into some more in-depth rocket theory related to design. So this is another kind of info dump, so I don't expect you all to remember everything. That's what the purpose of these slides is for you to go back and be able to review this.
So now that we've kind of established a baseline of what's in your rockets through hands-on experience and all that, we're going to sort of open the doors to your creativity. And so the idea now is to sort of scale up a bit and work towards integration with the other intro tracks. So throughout this presentation, we're basically going to outline like key skills that you would need to focus on in the design of this larger scale rocket. So this is just something fun you can do. You now have free reign of your fins. Ideally, we'll have equipment to actually make these now too, once we're actually getting to that. So Andy, I'm going to steal sharing screens really quick just to share my open rocket. Here's open rocket. I just have a tube laid out right now. If you click on this button, freeform, you can click on shape and you can make this basically as custom as you want. So you can drag these points around or you can add points just by clicking anywhere else. So if you want to make like really cool jagged design or something like a TIE fighter or something, you can totally do that. And so this is just something fun for you guys to think about. We're really starting to open up the creativity now. So yeah, have fun with this, start messing around with your rockets. And this is something that exists, just to plant it in your mind.
When you go out the launch trail, just as with all your video games and with all of your TV shows and everything, you want 60 FPS, which of course means feet per second. That's also about 41 miles per hour. I think it was 18.3 meters per second. So you want it to go really fast, because if it goes really fast, all the air will hit the air and it'll make it go straight up. What you don't want to do is exactly what we have in the picture, because that makes your rocket go, A, not as far as you intended, but B, off in a really weird direction, and you don't want that. We may or may not have had members of this club try to climb up trees to try to get rockets out of them, / had to call tree services to get our rockets back. That wasn't because of this, it was because of wind, but this only makes things worse and a bunch of bad things. So you don't want that. You want it to go straight up. And then this 5-to-1 thrust weight ratio, that's a minimum. And that's why for bigger rockets, you want bigger motors. And that's why you have to prove yourself with smaller rockets to be able to buy bigger motors. To achieve this 60 feet per second, you really want a 5-to-1 just to be safe. And again, all these are minimum, so you want to be over this.
The cal rating, it's short for stability caliber, it's the distance between the center of pressure of the rocket and the center of mass divided by the rocket's diameter. So that distance between the center of pressure and the center of mass, that's largely determined by where you put the weight in the rocket and how big your fins are. So the bigger your fins are, the farther it'll shift your center of pressure back in the rocket, like down towards the tail. And the obviously, like the more mass you stick in your nose cone, the farther the center of mass goes towards the nose cone. So if you stick a bunch of mass in your nose cone and you make your fins really huge, then your center of mass and your center of pressure are going to be very far apart, and you're going to have a large cal. So the thing there, though, is that the motor is a pretty significant weight in the rocket usually, but the motor goes away during flight. So that essentially, so the motor is situated back down towards the tail, right? So if you get rid of the motor down there, it'll shift the center of mass forward in the rocket towards the nose cone, away from the center of pressure down by the fins usually. And that will increase the cal. So that'll make it more responsive to deviations between the axial direction and the velocity of the rocket. So that's essentially that 2 cal rule of thumb. That's sort of, or we have it here as 1.8 to 2.8 for starting off with. That's including the mass of the motor, and that takes into account the fact that that motor mass will go away. So don't design the rocket so that it'll have a cal of 2.8 without the motor. So yeah, just something to keep in mind. If the cow's too high, it might cock into the wind too much. It might wiggle around too much in flight, and obviously if it's too low, who knows what'll happen? It might be very bad. It might end up going in all sorts of directions.
All right, so I'm going to talk a little bit about shock cord. So the shock cord is the rope that connects different sections of your rocket together after a separation event. Normally these separation events in our club are driven by black powder charges, which provide enough force to physically break the sections apart. And the two major material options that I've had the most experience with in the club are nylon rope and Kevlar. And nylon rope is, you can see in the top left, it is very elastic and resistant to shock loads. And Kevlar is an aramid, which is very strong as far as length goes. Roughly 3 times the overall length of your rocket is a good rule of thumb for the amount of shock cord per parachute. And unless you have like an extremely thick shock cord that has, you know, a lot of added mass and volume, you can generally fit this length of shock cord per parachute. And you'll be surprised, there are some really heavy and really high strength shock cords on the McMaster car rated for like 3,000 pounds of shock force. It's a much higher rating than anything you would probably need in the club, but those cords do exist. So if you go with that option, you definitely have to consider mass and volume of the shock cord itself. Placement of the parachute along the length of the shock cord is something to consider as well. You can see in the bottom right diagram, you want to space the shock cord, or you want to place the parachute along the shock cord so that sections of your rocket after separating don't necessarily like knock into each other or collide during that period where there's a lot of force, a lot of aerodynamic drag happening on the rocket. And you generally just want to separate the sections of your rocket by a reasonable distance so that there's no chance of your rocket damaging itself upon separation. And kind of the last thing that I've learned about shock cords is that after repeated flights without changing out your shock cord, there's a chance of the shock cord becoming like crispy or degraded over time. And this is because during an injection event, there's a lot of hot gas produced and it can weaken the shock cord over time. So if you notice your shock cord, say, becoming kind of crispy or visibly kind of like weakening, you want to replace that. And it's simple enough, to tie a new piece of shock cord onto your parachutes. So that's something to consider as well.
So after shock cord comes parachutes, my personal favorite part of the rocket. We've talked about parachutes a lot in terms of, you got to make sure your rocket comes down safely. So a couple things about parachutes. There are a lot of different sizes, there are different shapes, and both the size and the shape affect the amount of drag it has. So drag depends on something called the coefficient of drag, which is just like a constant depending on the shape of the parachute and on the area of the parachute. And a couple of other things. It depends on speed. We'll get into that later on. But in terms of sizing your parachute, those are the things that matter. Next component that's important on a parachute is the swivel, and that's circled in that lovely image there. And that makes sure that your parachute lines don't get tangled during descent, right? So when the chute comes out, the rocket's falling, the chute's flying everywhere. It's a pretty chaotic moment, and the chute will sort of twirl around in the air. And so the swivel makes sure that the chute can twirl and the rocket cannot twirl, and those two things will not get tangled together, because if your parachute cords get too tangled, the chute can't open all the way, and then it won't work as well or at all. And then your rocket hits the ground hard and you're sad. Other important part of a parachute rigging system is the Nomex cloth. That's upper right there. And that's just a fire retardant cloth that you wrap around the parachute when you pack it to protect it from the black powder charge, because you are basically making a small explosion inside of your tube to separate the rocket. And the parachutes are made of really thin nylon material, so they pack small. which is very good for that. And they're nice and lightweight, but they are not fire retardant. So if they get hit directly by the black powder charge, you can burn a hole in your parachute, which is not great because then there's a hole in your parachute and it's not obviously working as well as it should. So that's why Nomex is important. And you just tie the Nomex right onto the shock cord pretty close to your parachute when you're packing it. Yes, so now that you've chosen your parachute and got it all rigged up, you need to pack it, right? And this is another thing that's important to make sure your lines don't get tangled, is to pack your parachute sort of neatly and carefully. You don't want to wrap the shock cord around the parachute. You want to sort of fold it up. A lot of parachutes have sort of different color stripes, and you could use that as a folding guide. And when we actually do this, we will teach you how to fold a parachute, like actually in person. But this is sort of a rough guide of the steps that you should follow for that. The other thing to watch out for is that you don't want to get it too stuck in the tube because it does need to be able to be blasted out with the black powder. You don't want it to get stuck. We had that happen once and it was very sad.
So yeah, the point of the parachute is to limit your ground hit velocity so that your rocket isn't damaged when it hits the ground. It'll also hopefully prevent your rocket from damaging things on the ground, like houses or whatever. Hopefully you're far enough away from houses, but you never know. So there are various ways to sort of quantify the amount of damage that'll be done to your rocket when it hits ground. One way is to look at the kinetic energy. You could also look at the momentum. And if you really cared, you'd quantify the springiness of the ground and actually figure out the some kind of curve of force over time. But we never do that. It's not necessary. But what we do usually do is keep it under 20 feet per second. And 15 feet per second is very safe. And for most of the materials we'll be using, that's fine. You won't have any issues there. Now, you might think that, well, you know, you should just make it as low as you can go. But the problem is that if you make it, the lower you make it, the longer it takes for the rocket to get down to the ground, right? So during that time that it's traveling down to the ground, it will be moving horizontally with the velocity of the air around it, because it'll just move with the air. And so if you have a big wind, if you have, you know, say a 10-mile-an-hour wind, or here, we'll call it 10 feet per second, that's easier. And say it takes, you know, 20 seconds for your rocket to get down, then it's traveled 200 feet sideways, right? So you know, depending on your launch area, your launch site, you know, what's in the vicinity, that horizontal travel might not be acceptable. Also, you just don't want to have to go chase after your rocket too much. Might make it hard to find if it lands in some bushes or something like that. So yeah, you want to minimize the descent velocity while minimizing drag minimizing horizontal travel at the same time. And there's a trade-off there, obviously, and it'll depend on your launch site and other constraints and dangers and obstacles. And also how high you go, because the higher you go up, the longer it takes to get down, and the farther you'll drift. So for parachute sizing, that's what just determines, along with height, how long it takes for the parachute to get down. So obviously a larger parachute will catch more air, and it'll take longer for the rocket to get down. And a smaller parachute won't catch as much air, and it'll go faster, and it'll get down sooner, but it'll hit the ground harder. So the measure of sort of how much the parachute catches the air is the coefficient of drag. That's the variable is called CD. You can see that here. And the coefficient of drag is defined in terms of, usually for the parachutes we use, it's defined in terms of the area of the parachute, or sort of the projected area of the parachute when it's open. So if you take a plane and project the sort of the silhouette of the parachute onto the plane and look at that area. So say if you go and buy a 48-inch parachute, then the radius is 24. So then it'll be 24 squared times pi. That'll be the area. So if you want to calculate your descent velocity, that's v down here in this equation. You take the square root of 2 times the weight of the rocket and divide it by the coefficient of drag. And R is the density there. So that's 1.225 kilograms per meter cubed, right? Wait a sec, is that, yeah, that's right. And A is that's that area of the parachute. So for a 48-inch parachute, it would be 24 squared pi. So this is sort of a specific application of the general drag equation. One thing to consider is the shock loading when the parachute deploys. So when the parachute deploys, obviously the rocket's potentially going pretty fast, and then all of a sudden the parachute comes out and catches a bunch of air and slows it down really fast. So the acceleration there can be pretty high, and the force associated with that acceleration can be pretty high. And if your rocket isn't built strong enough, or if that acceleration's too high, it can damage your tubes, or even just rip right out. These graphs over here are for Project Redshift. We're messing with a system that allows one parachute to change its coefficient of drag several times during descent. So that's kind of fun. In this scenario here, there are actually sort of 2 deployment events during descent. So the parachute opens at apogee up here at time equals 0, and then subsequently 2 more bigger parachutes open. But you can see these changes in velocity here, and for these changes in velocity on this curve over here, there are corresponding accelerations and forces based on the mass of the rocket. So just something to keep in mind. And if you want to go and model this stuff, you can use MATLAB, but OpenRocket works just as well for most applications, although OpenRocket assumes instantaneous changes in the coefficient of drag. So essentially, it takes you from the drag force on the rocket at one parachute configuration, and instantaneously, from one data point to the next, it switches it to the drag force associated with the bigger parachute, or whatever you're deploying next. And that's unrealistic, because the parachute doesn't open instantaneously. The new parachute you're deploying, it doesn't open instantaneously. It takes a little while for it to open. So, and during that time, there is some drag on it. So it ends up slowing the rocket down a little bit during that time. So that essentially decreases the shock load on the rocket, the maximum force the rocket experiences. So take accelerations from OpenRocket with a grain of salt. Another thing to consider is that there may be some damping in the shock cord itself. The shock cord can help with minimizing shock load. So yeah, what OpenRocket gives you may not be accurate. It actually probably isn't. Yeah, it's never going to be accurate. But for the most part, you should be okay if you build sturdily, and we'll help you with that.
So yeah, sort of like we mentioned briefly earlier, the end goal here is to integrate with the other intro tracks. So you might have heard about mechatronics and intro avionics. They've basically been working parallel to you guys. And the grand scheme of things is to get them to integrate their projects into your airframes. So the idea there is to start that into the spring, and we're going to start designing those systems right now. Actually, we're going to break you guys into groups after the slide. So the way that we do that generally in this club is that we try to come up with general constraints of, hey, mechatronics wants to do something, and they'll give us like a black box payload. So that's what you can see listed down there. They'll give us these general dimensions and estimates on what the size and weight of the object will be. And then the airframe tries to build around that to the best of their ability. And then naturally, this is sort of a fluid process that tends to go through iterations. But as of right now, because we've already done all the discussion in the background, these are solid constraints. So right now, your rocket that you guys will be designing will be integrating a payload from Intro Mechatronics, which is supposed to be a rover of some sort. And for you guys, your constraints are going to be that it needs to be 12 inches long, 2 to 3 kilograms, and you need to have some form of parachute. It's going to have some form of parachute deployment system for it to hit the ground, basically. On the other hand, avionics has been designing boards that will be going into your rocket to handle flight events. So we'll talk a lot more about eBays in our next meeting. But the general idea of what an eBay is it's little chips that are there in your rocket to handle the flight events. So that's when you're parachute to deploy. So it's basically a combination of sensors and chips where your rocket is positionally, what altitude it's at, what speed it's at, what the acceleration is through a bunch of different methods, and then to deploy the parachute accurately based on that information. So avionics has gone ahead and designed a board that will be integrated into this rocket in particular, and it's going to be a dual deploy system. So Andy mentioned this a little bit earlier, but a dual deploy system is essentially that there's two parachute deployment events. So the first one is called the drogue. That's basically a really small parachute that's just meant to sort of gently guide the rocket down for most of its transition down. And then eventually, once you're much closer to the ground, you'll have your main event happen. And then the rocket will decelerate rapidly and you'll have the safe landing that we talked about earlier. So the idea here is that you spend most of your time descending at a fairly rapid pace so that you avoid drifting too far away. And then when you get close, decelerate at the most amount that you can. So that's the idea here. And yeah, that's what you guys have to look forward to. So it should be really cool seeing you guys work with groups and all that. But
yeah. And also, just to clarify, for this meeting, we're not going to be too stressed about, designing where the payload should go and all the eBay stuff. For right now, we're just going to treat the payload as a 12-inch long section. Technically, the payload itself will only be 8 inches long, and then the adapter will be 12 inches long. But that's getting into the nitty-gritty. And for the electronics bay, we'll be designing that in a future upcoming meeting in SolidWorks. So that's why we learned about that earlier on this semester. And we fortunately have a simple model or a stand-in model that we're going to use for the flight computer chip. So again, you don't really have to stress too much about that right now. Today's meeting, and Andy, you can head to the next slide, is basically just create the framework for a 4-inch diameter rocket